Good morning and welcome to this webinar on Practical SOA for the Solution Architect. My name is Ganesh Prasad. About myself, I'm working currently as a consultant architect with WSO2 and I've almost completed a quarter century in IT. I've been in Australia for the last 15 years working with very large companies in the financial services sector. And at least the last 10 years of my experience have been in some way related to SOA. I must say I've had a lot of experience working at end user organizations that have been implementing SOA projects internally as opposed to vendors. And I've had the good fortune of being on several design review committees and have seen a very large number of solution designs that were claimed to be SOA. And I guess many of the ideas for this lightweight method came out of that practical experience. Well, I guess this audience is, the target audience is quite generic. Anyone in IT with an interest in integration would probably benefit from this webinar. However, the main target audience is the solution architect. The solution architect is a person who is really key in the end-to-end development role, because the solution architect needs to understand business requirements as provided by business analysts. And they produce the high-level solution design, which is an outline solution, and that's further fleshed out and implemented by development teams. So really the solution architect is the person in the middle who is translating business requirements into an outline solution design. And as part of this job, the solution architect needs to identify existing components that can be reused, because quite often you don't build solutions from the ground up, you reuse what you have. And to meet a new business requirement, sometimes you may also need to build some new components. So you either need to buy or you build them. And most importantly, and here the devil's in the details here, the solution architect would need to specify how all these existing and new components are integrated to meet the business need. Right, so the solution architect really is the target audience for this webinar. But anyone else who has an interest in end-to-end solution design involving integration of large-scale applications and systems would also benefit from this. Okay, why do we call this practical SOA? Well, actually, SOA has been with us for a long time. It's been here for at least 10 years, and we've read a lot of literature on SOA. We've attended lots of conferences and done projects. We know products. So it's been with us for quite a while. However, many IT practitioners think SOA is a buzzword that has come and gone. And yesterday we talked about SOA, today we're talking about cloud computing, tomorrow it will be something else. But that's a bit pessimistic. Some people think that they understand the concept of loose coupling in theory, right? But when you look at the kind of solution designs they come up with, you realize that they haven't learned how to apply that concept in practice. And yet others think that just because they're using a SOA product from a reputed vendor, say something like an ESB, they are doing SOA. That's why in practice you find that many designs that are considered to be SOA based, running on reputed SOA products, are actually very tightly coupled, and that's against the very principle of SOA. So what we need to do is re-educate solution architects about what really SOA is. Again, it's a challenge to get busy solution architects to read the theory or sit in a classroom or even learn a heavyweight methodology. So what we need is an approach that is really simple to understand and easy to apply. That's what we call practical SOA. And I'd like to think that as part of this webinar, by the time you finish, you would have enough of an understanding of SOA to go off and work on a project that you're currently working on with a fresh pair of eyes, and you look at it and you say, now I know how to implement this using SOA. Okay, so diving into it, any solution design at all, we're not talking about just SOA here, any solution design really has two aspects to it. There is a technology aspect and there's a data aspect. You can look at them as two different layers. Now, with SOA, what's actually happening is the technology provides you many, many ways to decouple systems from each other. So the number of dependencies that you have between systems is drastically reduced at this level because lots of things get standardized. Wire protocols, data encoding, message exchange patterns, qualities of service, all of these are standardized to such a degree that you don't need to have artificial dependencies between systems. However, there are so many different tools and patterns out here that the challenge before solution architects is deciding which ones to use. What are the right tools and patterns to use for a given situation? The data layer is a lot more subtle. This is the application design itself. Now, SOA products will support you in doing this design, but you are responsible as a solution architect for designing this layer properly. And we'll look at this in more detail as we go along. There are some really subtle aspects here that could trip you up. And if you do not ensure loose coupling at the data layer, then all the investments that you make in the technology layer are negated, and they could be quite significant. So you might find that after spending millions of dollars on buying SOA products, you really don't get the benefits of it. All right, so diving right in, let's take this technology layer first. That's more tangible and easily understood. There are three core components at this layer, and only three. And they are the service container, the broker, and the process coordinator. And that sounds a bit like the butcher, the baker, and the candlestick maker. But what these three components are really is the first one, the service container. When do you use this? So you have a business requirement, and it demands a component that doesn't yet exist anywhere in your enterprise. You can't just purchase this off the shelf. You have to develop it in-house. And what you want to do is build this functionality in such a way that it can be used by many different applications. It's not something that is purpose-built for just one application. In that case, a service container is what you need to host this logic. So looking at this diagram, on the left you have a black box service consumer that requires this functionality. So you run this business logic inside a service container, and this logic is now exposed as a standard service that any consumer can consume. Right. But what really happens when you build large-scale systems is you're not going to write every single component from scratch. In practice, you will be able to exploit pieces of logic or pieces of data that already exist somewhere in your organization. So it's in some legacy system, some legacy application. But there could be some complications. For example, if this legacy component speaks a very proprietary protocol, then what you need is an adapter to translate from this protocol to a more open one before you can use it. Or it could turn out that the data that it contains is not in the right format for you. So you need a transformer to change this data somehow to a more usable form. And then again, you might need to hide access to this legacy application. You may have to proxy it, or in some way make it location transparent for any number of reasons. So you need a mediator of some sort. And in this diagram, what you can see is on the left, there is a black box service consumer that just needs a function. On the right, you have a black box service provider that has that logic or function in it, but it exposes it in a proprietary interface. So this broker component in the middle has an adapter that talks that proprietary protocol. It may have some transformer logic inside it, which can change the data that is exposed through that component. And then it exposes itself as a service, which is a mediator function. It hides the location of the actual physical service and so on. So that's the broker. And the third component is the process coordinator. Now sometimes you have a complex process to manage. There are many steps. Each of those steps is a service. And sometimes you don't know in what order those services must be invoked or which of them should be invoked. So there's something like a dependency on a runtime status that you need to check. So it's a dynamic requirement here. So the process coordinator is the one that can call on automated as well as human tasks to invoke at different steps in the process, and it can make these decisions dynamically. So in the diagram, you have a black box service consumer on the left. You've got some individual services on the right, and you have this process coordinator running some process logic here. So it invokes those process steps on the right in some order and deciding on which ones to invoke depending on a runtime status. And the whole process is wrapped up and exposed as a single service that can be consumed by a service consumer. So these are really the three core SOA technology components. There are also some supporting components at the technology layer. So the service container, the broker, and the process coordinator, these are quite sufficient for a basic solution design. But sometimes you can enrich and refine the solution with some specialized functionality. Right? For example, if you have specialized rules that need to be applied, normally a service container hosts process logic in Java or C# or some programming language. But sometimes this logic could be expressed in a rules-based paradigm. So a rules engine is something that is specialized and it helps you answer certain questions. So even process coordinators may rely on rules engines to decide what to do next. Similarly, you may have data access or data servers, which are a specialized form of brokers, and that interface specifically to data stores. So you might have your data in a relational database or in some proprietary data store of some sort, and rather than expose that proprietary API to your process, you would like to expose it as a standard service. So data services servers could do that. Registries are data stores that hold references to service artifacts. Repositories will hold the artifacts themselves. And these are normally used to give you a degree of control over all your service artifacts so that you then can build on top of it support for governance. Governance is basically putting in place the discipline that goes from development to operations. So you embed the very discipline of how you should do something and force it into the protocol of your organization's operations. And governance is usually based on registries and repositories, as well as certain additional tools that can be used as in your process. Once your system goes live, you would also need to monitor it to make sure that it's healthy, because quite often systems are victims of their own success. And you need to know when something is getting overloaded and be able to address those kinds of issues. And a more sophisticated form of activity monitoring is complex event processing. So sometimes you may want to monitor a set of events that occur within a certain window, and that combination might suggest something like a fraudulent activity, or something about to happen to the health of the system, like some servers about to go down because there's a spike in usage, or could be a change in customer behavior and so on. So complex event processing servers are a combination of process servers as well as rules engines. Most of these components are also hidden away in the back end, and they're not exposed to the user interface. But very often you need hooks into your front-end applications so that your user interfaces can easily invoke a lot of this back-end functionality. So you need presentation support to be built in to your SOA suite. And finally, even though we have glossed over it initially by saying we need to expose business logic as services, there is, of course, the caveat that you would not expose it to just about anybody or any actor. So you need to identify or authenticate your actors and then provide them access to specific services depending on access control rules. So your identity and access management becomes a key part of the whole service ecosystem. And just to make all of this concrete, let's have a look at a tool suite from WSO2. This webinar is not about WSO2's tool suite. It is on purpose. It has been made a very generic and it's a conceptual webinar. So you can apply the set of techniques to any vendor's tool suite. However, looking at what WSO2 has, you can see that the service container is probably something like the WSO2 application server. This is something that can run business logic in the form of Java programs and expose them as services, web services. Then you have the WSO2 Enterprise Service Bus, the ESB, which will act as a broker that mediates between different systems. You also have the WSO2 Business Process Server that can act as your process coordinator. It runs BPEL scripts, and in the near future, it will also be able to handle human tasks. And then you've got all of the other services that we talked about. You've got the Business Rules Server, you've got the Data Services Server, and so on. So here's what a full tool suite would look like. And you get these tool suites everywhere, right? For IBM or Oracle or TIBCO or Microsoft, all of them would provide you these components. The important thing is to understand what these core components are in generic terms and when to use them. So the service container, the broker, the process coordinator are your three core components, and you need to know when you use each of them. Okay, there are two common mistakes that are made at the technology layer, and both of them relate to the broker. Right? The first mistake is that when all you have is a hammer, the whole world looks like a nail. And this is commonly referred to as ESB-itis, like conjunctivitis or tonsillitis. ESB-itis is a medical condition where the patient believes that an ESB is the solution no matter what the problem. Right? These ESBs are quite powerful, really. They have lots of extensions. But don't use it in place of a service container. In other words, don't host business logic on a broker. A broker is meant for mediation. If you've got logic somewhere else in a legacy form, then use the broker by all means to mediate access to it. Don't put the business logic on the broker. Business logic, if you are writing it and hosting it, it belongs in a service container. Similarly, even if it's possible for you to write some coordination logic and put it on a broker, that's the wrong place to do it. Coordination of processes belongs in a process coordinator. You might be able to stretch a broker and make it do it, but typically that would lead to some tight coupling, and it might also impact the performance of the broker. So use the right tools for the job, and if you ever find that you're hammering in a nail using a screwdriver, drop that and pick up a hammer instead. Ensure that your developers are equally proficient in the use of all the three core SOA components so that they are able to use the right tools for the job. Very often you would find that developers would use one tool over the other even if it's not appropriate, just because they happen to know it. The second common broker-related mistake is using it in a hub and spokes kind of architecture. A broker is not really a singleton, a centralized component. Probably what's happened is many commercial brokers are very expensive. So there's a temptation not to use more than one or two of them. Just keep one instance of the broker right in the center of the enterprise and route all traffic through that. And you might actually have two instances of it for load balancing or for availability sort of thing. But it's not really necessary to do this, because there's nothing in the functionality of a broker says that it should be hosted in the center, because there are implications, right? There is a performance problem because this becomes a bottleneck. All traffic is going through a single node. There is a performance bottleneck, so that impacts your scalability. This is also a single point of failure. So if your broker now goes down, your entire operation is grind to a halt. So availability is also impacted. What you should be using the broker as is as a federated broker in a decentralized model. So in this diagram, what you have on the left is a service consumer that is trying to invoke some business logic. Now this business logic is actually controlled by a process coordinator in the middle. The process coordinator is invoking 4 different services. 2 of them are bespoke services that you had to write and host inside service containers. 2 of those services already exist in your organization inside some legacy systems, and you need to mediate access to them using brokers. So you might have 2 brokers there at those endpoints, exposing those services as open services. Now once all of these services are coordinated into a process, the process itself is exposed as a service. But this legacy service consumer is unable to directly consume this open service. So it needs a broker on the consumption side to be able to talk its protocol to the broker, and the broker can make an open service call to the process coordinator. So you can see that the brokers are actually decentralized. They're pushed out to the endpoints. They're applied close to where services are either provided or consumed. Okay, so that sort of covers the technology layer. If you've understood that there are 3 core components and we know when to use each of them. Let's look at the data layer. And this example is meant to show you how subtle data design really is. Okay, let's look at an application, a business application that your organization has purchased off the shelf. And this application has got a lot of structured data inside it, but you also need to store documents or files alongside the structured data. So as an example, if this is an insurance company, and this system is a claims processing system. In addition to its database of structured data, it might need to hold, say, photographs taken of some damage as part of a claim. So where would you hold the photographs? Similarly, if this is a bank and it's a loan application system, then a person might apply for a loan and all their data might be in the database, but they might also submit scanned versions of their salary certificates, and that's an important document to be attached to the application. Where do you hold these documents or files? The application itself does not have the ability to store files. What you normally do in such cases is you rely on an enterprise content management system, an ECM system, to hold documents. And what the business application does is it can hold references to those documents as part of its structured database. And what you do in that to make this work is when you check a document into the ECM, it will return a document ID. So you store this document ID in the business application, because that's a piece of structured data it can hold. And similarly, when the business application requires to retrieve a document, it should pass back this document ID to the ECM, and the ECM will return the document. So the question is, clearly, looking at the diagram, you have a business application on the left that knows how to make certain service calls. The ECM service on the right offers a certain piece of functionality, but it speaks a proprietary API. So looking at what we just discussed at the technology layer, we know that the correct component to use here is a broker. You wouldn't use a service container because you don't have to write that logic yourself. It's already there. And this isn't really a complex process. It's just a straightforward mediation. So you don't need a process coordinator. You use a broker. It speaks a proprietary API to the ECM system. It exposes the common or a standard service internally that the business application can consume. So looking at this design, does this look right? A business application checks in a document. The broker calls the ECM system to check it in. The ECM system returns the document ID. The broker passes it back to the business application. The application stores the document ID. When the application wants the document back, it passes in the document ID. The broker passes it to the ECM system. ECM system retrieves the document, passes it back to the application. So you might think of the document as being streamed through it, but in practice, probably what happens is it gets copied to a different file location, and that location is passed back. Anyway, does this design look reasonable? Well, it is actually a very simplistic design from a data layer. And this is for many reasons. The first is that if you think about the document ID, this is something that is specific to an instance of that ECM system. And an organization might have multiple instances of ECM. Now, each one of them has document IDs. So the same document ID might refer to different documents on different instances of ECM. So it's not really a global reference. So which one do you imply? But now what this means is that when a business application says, I am storing a reference to document ID 1234, it also needs to say on ECM instance 5. So that ECM instance ID is an implied piece of information that the business application needs to store somewhere, maybe as a global variable or something. And probably that's how the solution design works. So the ECM, the business application is built so that it holds a reference to one ECM instance. And over a period of time, this becomes an assumption that every business application will be associated with one and only one instance of ECM. Now, there's another requirement as well, because when a document is checked in, it's checked in along with some metadata. Now, the metadata needs to be transformed in some way by the broker before it's put into the ECM. What kind of transformation logic should be used? That depends on the business application. So the broker needs to apply different transformation logic depending on which business application is calling it. But you've just made an assumption that an ECM instance is associated with a business application in a one-to-one relationship. And you are passing in the ECM instance ID to the broker. So some smart designer decided that, hey, we're getting the ECM instance ID anyway. Why don't we treat that as a surrogate for the application itself? And we can do our metadata transformation based on that ECM instance ID. So all of these decisions look quite reasonable, but the implications are quite severe. The first implication is you end up with too many instances of ECM, and this has license implications as well as operational cost implications. You don't need to have 20 instances of ECM to support 20 business applications. Maybe 5 would do. Right? You've got a second problem, which is that sometimes you've got high volume applications that are pushing through a very large number of documents, and it swamps a particular ECM instance. And what you'd really like to do is put 2 or 3 instances of ECM in some round-robin configuration behind an application so that when it's pushing through documents, they can share the load. But now you can't do this, because what you've done is implicitly in your solution design, you've said an application holds an instance to holds a reference to a single ECM instance. So you can't now hold 3 references. The converse problem is you can't share an ECM instance between different applications. Sometimes you have applications that don't actually have very high volumes. An application might only save about 100 documents a day. So and if you have 3 or 4 applications like that, you might say, why don't you just share an ECM instance? Unfortunately, we can't do that, because we are assuming that the ECM instance ID is a surrogate for the application, and you're doing your metadata transformations based on that ECM instance ID. If 4 applications share an ECM instance ID, then you can't do 4 different types of metadata transformation, which you need to. So you're stuck there. You can't move a document from one ECM instance to another, because the document ID changes. And the document ID is now being held by a business application. So if you ever move a document from one instance to another, you have to go back to the business application and say, can you please update this reference? Which is a pain. And you'll be disrupting business operations by doing that sort of thing. And that has further implications, because quite often you might want to implement some archiving strategies. You might say, my most frequently accessed documents, very few in number, can be held on this ECM instance, and I'll hold all the older documents that are less frequently accessed on that instance. And over a period of time, I just keep archiving or moving documents across as they get older to the older instance. But now, as we know, we can't do that, because every time we move a document, we have to go back and update the business application, which business people wouldn't like. So, as you can see, this is a really tightly coupled solution. It's not SOA compliant at all. But if you look at the technology layer, it seems to be the right component at the technology layer. You used a broker, and at the end of the whole thing, you haven't got a SOA compliant design. This is really sad. And in fact, this is very disheartening, because what looked like an open and shut case is not that simple. So, this can be quite disheartening, as I said. You might start off thinking that SOA is easy because it looked really simple at the technology layer, and most of us stay there. We're looking at technology products, and that's how we build solutions. And all of a sudden, we're turning out designs that are tightly coupled, and therefore we're not going to get the benefits of SOA, which are agility, low cost, low risk. This is actually a very, very rigid solution that is high cost. All right. What would be a good solution design for this example? There are many possible ways of skinning this cat, but here's one of them. Right? Instead of the business application directly calling the broker, it could call a process coordinator instead, because this is actually a multi-step process if you think about it. You have to remove the implicit knowledge of which ECM instance to go to from the business application. So it should no longer say, I know I'm going to store my documents on ECM instance number 5. It shouldn't know that. It shouldn't have to know. What it should say is, here's a document, here's the metadata, please check it in and then give me the reference. That's all it really needs to know. And the process engine would say, all right, now the first step is to find out which is the right ECM instance for this. And the right component to consult for that is a rules engine. So it goes to a rules engine, passes in the metadata of the document, and the rules engine is able to work out, oh, if this is the description of the document, this kind of document would need to go to that instance of ECM. And it could also be able to say, it appears like this is from this business application, and therefore you need to apply this transformation logic. So the rules engine will be able to tell you the correct ECM instance and the transformation logic required. So that's not something that you need to hold in the business application anymore. So having got this information now as an explicit piece of data from the rules engine, the process coordinator can now go to a broker and say, now check this document into this ECM instance and apply this transformation logic. So the broker can go off, talk to the that particular ECM instance, check in the document and the metadata, and get back an ECM instance specific document ID. And it passes that back to the process coordinator. The process coordinator says, not so fast. I'm not going to pass this instance specific document ID back to the business app because that's coupling it very tightly to that instance of the ECM. What I will do is I'm going to generate a globally unique ID and I'm going to map these two together. So I'm going to say this document ID and ECM instance ID combination is going to be mapped to a globally unique ID that is absolutely meaning free. And I'm going to store that mapping somewhere. And I'm going to pass back that globally unique ID to the business app. That doesn't mean anything by itself. And the way I store this, it's in some data store, could be a relational database or something else, but I don't want to mess with the details of SQL or any other proprietary access method to a data store. So I'm going to expose it as a data service. So that's what the process coordinator would do. It'll talk to a rules engine, talk to the broker, talk to a data service, and then pass back to the business application a globally unique ID. So now the business application is just going to hold that globally unique ID in its database. And if it ever needs a document, it's going to come back with that globally unique ID and say, please get me the document. The process coordinator will look up the data service and say, all right, now I know which ECM instance it's on and what the document ID is on that instance. It will go and talk to the broker. The broker will talk to the ECM, its proprietary protocol, and it will go back and get that document back and pass it all the way back. Now look at this. We can do all the things that we tried to do before. If you want to, you can reduce the number of ECM instances based on aggregate load rather than per instance, per application load. If one application requires 3 ECM instances because it's a very high volume application, the rules engine can be modified to do that. So you can say, if it's this application, spray the load onto 3 different ECM instances. And similarly, if you need to share an ECM instance between applications, the rules engine can do that too, because the transformation logic is independent now of the ECM instance. And if you want to move a document from one ECM instance to another, that's really easy, because all you need to do update is your mapping table. The actual meaning-free, globally unique identifier that the business application is holding doesn't ever have to change. And so the business apps are completely isolated from any changes that you make internally. So this is a much more loosely coupled system at the data layer. So what have we really learned in terms of lessons? Can we extract from this some generic principles that we can apply and ensure that our data designs are also loosely coupled? Well, there are 4. The first one is you need to identify dependencies between systems. Some of these dependencies are explicit, some are implicit. Now, an example of an implicit dependency in this example was that of the ECM instance ID. We didn't know when we first described the system that we would need to know which instance of ECM we were going to. That was an implicit dependency. Now we need to make all of these implicit dependencies explicit. That's the first principle. And the way we did it in the later example was to put that in a rules engine. To ask the rules engine, tell me which ECM instance, and you get that back as an explicit piece of data rather than just hold it as a global variable somewhere on the business app. The second principle is you need to eliminate unnecessary dependencies. Now, unnecessary dependencies come about for very good reasons, but they're usually historical. So if you ask somebody, why are you passing this piece of data? They might say, 2 years ago there was another system that required that piece of data and that's why we're passing it. Today that system has been decommissioned, but we still need to pass it because it's too much trouble to remove it. That's an unnecessary dependency. And in the example we just saw, an unnecessary dependency was that between the transformation logic to be applied and the ECM instance ID. There is really no dependency there. It was just that a one-time assumption that there was a one-to-one correspondence between the business application and the ECM instance ID. That assumption drove this dependency. So now you're stuck with tying your processing logic to the ECM instance ID. You need to break these instances of unnecessary dependencies. It's not always easy to do because these cost money. They take time. People complain. There's risk. Why break something that's working? It's not always easy to get business case to clean up an interface with no business benefit. But you need to be opportunistic about this and document all the examples of unnecessary dependencies that you can see. And whenever you go in there to make a related change, take the opportunity to remove these dependencies. Because the less the dependencies, the easier it becomes to change systems without affecting other systems. The third lesson is you need to map your domain data to message data. What do we mean by this? Domain data is data that's held inside a system. Message data is data that is found on the wire going between systems, especially data that is exposed to service consumers. And the example of this was the document ID. The document ID in the system was specific to an instance of ECM, and therefore it was domain data. And if this domain data was directly exposed to business applications, that's tight coupling. So you can't ever move this document out of that instance once you've exposed it to a business app. You need to map the two. That's what we did. We created a mapping table that held a meaningless ID and mapped it to this instance-specific ID. And that meaningless ID was what we gave to the service consumer. So we loosely associated message data with domain data. And there was no way to derive one from the other. Because if you can derive one from the other directly, that's again tight coupling. So that's the third principle. Now the fourth principle isn't immediately obvious from this example, but that's around developing a sane data model. And you need to go for an intermediate level of granularity. And I'll explain what this is. Let's take a bank. A bank typically has different divisions. Let's say there's a retail banking division that deals with deposits, loans, credit cards, and so on. Then there's an institutional banking division that does treasury, bond trading, foreign exchange trading, risk management. And then you've got wealth management, which looks at mutual funds, portfolios, or wrap products, and so on. But they are completely different businesses. It's just that they happen to be under the same bank. You will often hear this term, canonical data model. And the canonical data model says one vocabulary for everybody. So no matter who you are in this bank, no matter what system it is, it must all speak the same vocabulary so that any system can understand any other system. And this often goes hand in hand with the notion of the centralized broker. You have one broker for the enterprise. And this broker will do all translations. It will translate from any proprietary data format into the canonical data model and back again to the proprietary data formats of any other system. So any two systems can talk to each other through the broker because it all gets translated into this canonical data model and then back again. In practice, this doesn't work. It's infeasible. So don't even go down that path because you will spend so much money and effort in trying to define this canonical data model that you won't even get there. You just burn a lot of money without getting to a result. What is far more pragmatic is to break up your larger domain into a set of smaller domains which are logically coherent. So you might look at retail banking as a domain or institutional banking as a domain, and each of these domains has its own little vocabulary that is more tightly cohesive, and it's much easier to define this vocabulary because it is a natural business by itself. So you're not artificially trying to bridge the notion of a retail customer and an institutional bank customer, which are really very different concepts. Now, if you can see this diagram in the middle, there is no canonical data model, there is no centralized broker. So you have now what are called domain brokers. So the domain broker is responsible for enforcing a common vocabulary upon the domain. So any system within that domain, when it talks through the broker, will expose its functionality in the form of services that expose this domain data model. And when you cross domains, you would be expecting to find a completely different data model. And that's as it should be. So within your domain, you can talk using your domain model, but if you ever want to consume a service exposed by another domain, then you will have to understand that domain data model. It's like if you go to France, you have to learn French. You can't expect the French to learn English for you, and you can't expect that there will be interpreters everywhere who will be translating to and from Esperanto. So that clearly doesn't work. So this is a much more pragmatic model, and as you can see, it also ties in very well with the notion of federated brokers. So you've got brokers that are pushed out to the endpoints that are specific to certain domains and that are responsible for mediating access to functionality within that domain. So that's the fourth of the four data principles that we need to know. Right. Let's very quickly, we've got at least 10 minutes, I think. Let's talk about some industry examples. Banking. Opening an account is a common one. What would normally happen is when you go to a bank to say, I want to open an account, the first thing they do is they verify your identity, and then they check their customer database to see if you are an existing customer. If you're not, they generate a fresh customer number for you. Otherwise, they retrieve your old customer number and then associate that with the new account that you open for you. Then they generate the new account number for you. And typically, this is on a mainframe system. So it's 30 years old. All of their accounts are on this mainframe system. The only way to talk to the system is over MQ. The only data formats it accepts are COBOL copybook based. So, it's an old system, but it works and they use it. Then if you're a new customer, then they need to requisition a card system and say, please issue an ATM debit card for this person and link it to the account. And if you're an existing customer, then you already have a card, but you need to link the new account to the card. And the card system is probably just 10 or 15 years old. It may even have a service interface, but chances are that the data model that it exposes is not the same as your organization's data model. That would be the complication there. The card system would then make a request to a PIN mailer to have your secret PIN securely sent to you. So that's really the business problem. And the way the solution design would look would be something like this. So you have your customer, you have your branch officer who is talking to the customer and trying to get the account set up. They have an account opening front end. So they have a front end application that captures the information and makes calls into all of the back end stuff. So what it really needs is presentation support. How do you make service calls accessible to something that is a user interface? There is only one process here, which is open an account. So there is a process coordinator that's running this account opening process, and it exposes it as a single service. So you pass in some data and say open account, it goes off and does a whole lot of things. What does it do? The first thing it does is goes and checks if you're an existing customer. So you've got a customer database there, and the interface into it is probably SQL. You would need to wrap that into a service. So you have a data service, and once you have the data service, you can make service calls to it and say, get me and see if this customer exists based on the name, based on the address, whatever. If the customer doesn't already exist, then you make another call into it saying, create this customer. And you get back a customer ID. Then you go and create the account on the mainframe. Well, obviously the mainframe only talks COBOL copybooks over MQ. So clearly you need a broker to talk to it, and you need a queue adapter in the broker. You may need to do some transformation within the broker between COBOL and XML. And then that XML becomes part of the service interface that is invoked by the process coordinator. So you call two different services on this. You create an account or you link a card to an account. And if this is an absolutely new customer who doesn't have a debit card before, then you make a call to the card system. Now, the card system does expose a service interface, but it's not conforming to your data model. So you can still, there's no protocol change that needs to be done. You don't need an adapter for this, but you need to do some transformation to the bank's own schema, the bank's own domain data model. And that is exposed as a service that the process coordinator can invoke. So there are 5 different steps in this process, and the process coordinator invokes them all in a certain order based on runtime status. So it checks certain things. If you're an existing customer, you don't need to create the customer again, and so on. And yeah, so that's basically it at the technology level. And obviously at the data level, you apply the same principles. You make sure that all of your dependencies are identified. There are no implicit dependencies. All of the implicit dependencies are made explicit. You look at the dependencies again and make sure that you eliminate all the unnecessary ones. You look at the domain data that's hidden inside each of these systems. Make sure it's not tightly coupled to the message data that is exposed on the wire. And you, in this particular case, because all of these systems are in the same domain, which is probably retail banking, you might have just one domain data model that all of them conform to. So that's a really simple example. A slightly more complex example is in insurance, where you need to provide a quote and then convert the quote to a policy. So the way the business model works is there's a customer who wants to buy an insurance policy, and they go to an insurance broker. This is a human broker, not to be confused with the broker that we talked about at the SOA technology layer. The insurance brokers typically have access to different insurance companies, and they can ask them for quotes on behalf of the customers. So if the customer says, I want to buy a home and contents insurance policy or a comprehensive car policy, this is something the broker would ask the insurance companies to quote on. So at an individual insurance company, there's a rules engine that would need to determine what the premium should be for a customer based on the customer's details and the product details. Most of the time, the rules engine would be able to say, yep, this is the premium you need to pay every 6 months or every year. Sometimes it's a borderline case, and the rules engine can't decide. So it escalates it to a human underwriter. The human underwriter then makes a decision on what the premium should be and communicates it back. And sometimes they might refuse to quote. Once the quote is provided to the broker, it goes to the customer from there, either by email or on the phone. And it also needs to be recorded on this insurance company's mainframe in case it gets converted to a policy later. Now, the broker's front-end application gathers all these quotes from the insurance companies and presents them on the screen. Once the customer says, I want to purchase this one, the broker places an order. Then the insurance company processes this payment through a payment gateway and converts that quote to a policy. And this is what it would look like. This is more complex for two reasons. One is there are two processes here. There is a get quote process and there is a purchase policy process. The other complication is that there are human beings involved with this process. Unlike in the banking example where there were all automated systems that could be directly invoked, here there are humans. And the characteristic about humans is they may not always be online and they don't respond in the times that are expected by automated systems, which typically is second or sub-second responses. So the way you interface with humans is through inboxes. So you put a request into their inbox, they process it at some point, and then they put their response back in an outbox or in someone else's inbox, or they invoke another service. So there's some mechanisms that are required here for this system to work. So let's just go through this very quickly. The broker has a front-end application that again calls a process. So the first process is around getting quotes. So the get quote would go to a rules engine and say get the quote decision. If it gets a quote straight away, then that gets put into the broker's inbox, or it's directly displayed on the broker's screen. But if the rules engine says, pass, I need this to be escalated, then that reference goes into an underwriter's inbox. And the underwriter's inbox is front-ended by data services. So that's the service that the process engine calls. Then the underwriter has a front-end application. So when they come into work, their front-end application makes a service call into the data services of the inbox to get all of those referrals. And then when they make a decision on them, they update the decision on that inbox. Then the process server would again go back to this inbox and get the decisions. It would make a service call to get all the decisions that have been made, and that would feed back into the broker. The broker may not be online at this point in time, so those quotes that have been provided are notified to the broker by putting it into the broker's inbox. And again, that's front-ended by a data service. When the broker comes online, their front-end application would make a call into the inbox through the service call, get all the quotes. And once they display the quotes on the screen, they can then show it to the client or call the client and tell them these are the quotes they've received. And then the client comes back and says, I want to buy this one. Then the broker front-end application makes a second service call into another process that says purchase a policy. And the purchase policy goes to a backend system, which is the payment gateway, which is front-ended by a broker, and they make the payment. I forgot to mention, in the previous process itself, the quote is registered on the mainframe. So the mainframe, as before, like in the case of the bank, it only talks COBOL over MQ. So you need a broker that has a Q adapter and does COBOL XML transformation and exposes a service called register quote. So your quote is now registered on the mainframe, and now when the customer is buying the policy, once the payment is made and a successful status comes back to the process coordinator, it then makes a service call into the broker, front-ending the mainframe to convert the quote to a policy. And that's how a policy is purchased. And once again, you need to look at those four data principles. And the fourth one, again, because it's, again, one domain, it's all underwriting. So you may not need more than one domain model. It's just one domain data model. So to summarize, the success of SOA depends on the solution architect, because the solution architect is the one who converts a requirement into an outline design. And the solution architect needs to pay attention to two layers, the technology layer as well as the data layer of the design. At the technology layer, you need to know the right tool for the job. Use a service container when you're writing logic and exposing it to other applications as a reusable service. Use a broker when you already have that logic or data in your system but not accessible directly. Use a process coordinator when you need to coordinate multiple steps of a process and you don't always know the order of those steps unless it's at runtime. And you can supplement these three core components with supporting components, the eight supporting components that we saw. There are two common broker-related mistakes. Stay clear of them. Use the right tool for the job again, and don't think of the broker as a centralized component. At the data layer, there are four principles. Make your implicit dependencies explicit. Put them in a contract. Remove unnecessary dependencies whenever you can. Loosely couple your message data with domain data. Don't derive one from the other. Map them. And choose an intermediate level of granularity for data models, neither too coarse-grained nor too fine-grained. And we had a couple of vertical industry segment examples that we saw to make the concepts real. So now you have understood practical SOA. You know the principles, you know what to use at the technology layer, you know what principles to apply at the data layer. Hopefully when you go back to work in the next 10 minutes, you can immediately start applying these principles in your day-to-day work. Thank you. I'll take your questions now.
Thank you very much, Ganesh. So folks, as mentioned, you now have the chance to send in any questions or clarifications with regard to today's session. I can already see that quite a few questions have come in during the past hour. So Ganesh, I have forwarded them on to you. Maybe you can start answering now.
Yep, I can see a few questions here. I've got 6 questions here. The first one says, is a process coordinator different from a process orchestrator? No, it's not. It's the same thing. We just wanted to use generic terms rather than any product-specific terms, because you might have some vendor product that calls it a process orchestrator. Process coordinator is just a generic term for it. So process coordinator is for orchestration? Yes, that's right. That's the second question. The third question was, there is a recommendation that services deployed in service containers should be mediated as well. Well, okay. If you are building a service yourself and you know your domain data model, you would probably deploy it as a service that conforms to that domain data model. So it wouldn't need to be mediated. However, depending on the what we talked about with multiple domains, is you've exposed it as a certain through a certain domain data model, but there may be an application that lives in another application domain that wants to consume this service. So definitely, because they speak a different data model, some mediation would need to be done. And that mediation may need to be done close to the consumption point rather than close to the service provision point. So you're right that sometimes service containers may need to be mediated as well, but I don't know if it's something like a hard and fast recommendation that you always should mediate them. Any rationale, the fourth question was, any rationale on why it is impossible to find a canonical data model? A canonical data model is a very seductive idea, and I think it's not so much of a rationale why it's not possible as it's hard experience. Through empirical evidence, we have seen that not many people have succeeded in getting success with a canonical data model. You do have, data models. For example, IBM's IFW for banking or IAA for insurance. They are pretty good data models. They are quite generic. But if you look into the details of it, you would find that sometimes they are very high level. And if you want to apply them in your system, it takes a lot of work. Similarly, the Accord standard for insurance is quite a nightmare to implement. And sometimes the pragmatic approach is to use your own simpler domain data model within the organization and only speak Accord to other organizations, because that's the only way you can agree on a standard. So that's really why the canonical data model doesn't seem to work in practice. Deploy services in service container. Other than deploying web services to an app server, what are the other real-life implementations? Well, rules engines are a specialized kind of service container. Then WSO2 has an interesting product called a mashup server, which you should look at. The mashup server can be used as a service container, it can be used as a broker, it can be used as a process coordinator. It's actually, you can write stuff in JavaScript, and because JavaScript has this very nice extension called E for X, ECMAScript for XML, you can do very simple XML transformations, XML manipulation using JavaScript. So this mashup server is something that it's not possible to easily categorize as either a service container or broker or process coordinator. So that's something you could look at. That's a real-life implementation that would give you some interesting examples. Okay, another question is, if my use case is to notify an application of an event that happens in a different application, what will be the framework for accomplishing that? Okay, now, so you've got different standards as well for this, right? So you've got WS eventing, which is an eventing standard, and that because it depends. I didn't want to get into the details of SOAP and REST and different implementation technologies, but there are different technology-specific ways of informing components about events that have happened. And I think at this level, it's enough to say that any system that conforms to the WS eventing standards in a SOAP WS star kind of environment would use that notification mechanism to accomplish it. So I mean, you need to go into much deeper detail to explain how that works. But WS eventing is probably what you're looking at in the WSO2 context. The next question is there a theoretical base of SOA available at the WSO2 site? Not quite sure what this question means. Theoretical base. Well, there is enough theoretical literature about SOA available anyway, and it's not just at WSO2. What you would find at WSO2 is a number of use cases pertaining to the use of the different components in different contexts. So there's a very large number of use case examples. So if you want to do, say, JSON to XML transformation, there's a specific example for that you can run on your ESB. And so for almost every product, they've got a number of different examples that you can straight away download and run. But theoretical base, I'm not sure what you mean by that. If it's literature, then you don't really need to go to WSO2 to get SOA literature. It's available all over the web. The last question on my list is, some products provide the facility to host a service in the ESB. Hosting the custom logic in the broker, is that a bad practice? Yes, it is, unfortunately. Looking at it from the perspective of the ESB vendors, they're trying to make your life as simple as possible. So if somebody says, I want to host logic in the ESB, they'll say, sure, sir, you're the customer, you're always right, and we'll make it possible for you. That's not really good practice. And I've seen this happen myself. When you have developers who know how to use the ESB, and the ESB allows you to host logic written in Java, then you can pretty much do anything. You can host services on the ESB, you can write coordination logic in Java and host it on the ESB, and so the ESB becomes a process coordinator. And these are exactly the kinds of things that you shouldn't do, because that's not the way the tool is meant to be used. The broker is the mediator. It's not a service container. So that brings me to the end of my list of questions. Are there any more? There's one more. An application A is connecting to application B and sending data by FTP. Now, to create a service client and service provider on either side to facilitate duplex communication seems a lot of ball and chain. Any comments on it? So first of all, I think you need to go top down and say, what is your data dependency? So you're saying it's sending data by FTP. Is FTP really a part of the requirement, or is it just the way it's being done today? That's really the crux of it, really. If you're saying, why are we sending data by FTP, that might actually tell you that it's not required. Maybe there's another mechanism to send data. If FTP is really a part of your requirement, then your analysis will be different. So that's my first question would be, why do you want to send data by FTP? Is it just a store and forward mechanism? Is this, because a lot of applications do this. it's too difficult for them to use a message queue or to make an HTTP call. So the simplest thing to do is drop a file in a file system and have a file watcher. It's just legacy. It's just the way people tend to do it because they are familiar with that method. And as a solution architect, you need to ask if that is really the best method to do it, or can you make use of some of these more modern tools and transport mechanisms to achieve this integration. Okay, I've again come to the end of my list of questions, and I think we're over time as well.